Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hey, my name is Heiko. I just started a PhD at the Gatsby unit in London, do research in neuroscience and machine learning, and I'm going to talk to you about an open source machine learning toolbox called the Shogun Machine Learning Toolbox. So here's some small bits about Shogun. So we're an open source toolbox. It got initiated in 1999 by Gunnar Retsch, who's here, and a student of his, or kind of his back then, and the library first made public in 2004, so it's it's been around for a while. But these days it's more of an open source community project, so there's no big group or big company behind it currently. But we have like 8 core developers that are kind of constantly, active every day, and about 20 people that are active on a weekly basis or something like this. Yeah, and I want to emphasize here, because most of these projects have kind of these super high profile supporters. We don't have this, we're just an open source project. What mainly drives us, where our manpower comes from, is from Google Sum of Code, where we have quite some impact. We've done 29 projects so far. This year's Sum of Code just ended on Monday. I'm going to talk a bit more about this in a bit. I don't know if you know the website Ohloh. That's like a little data mining website that crawls GitHub and produces statistics. So we have 126 people who have contributed code. This is lines of code without comments. With comments, we just hit the million. We've written in C++. I like this comment here. I'm going to talk more about the how you interface with the library in a bit. But I like these things. They estimate how the development intensity, how stable it is over time. So we have active development over a long time now, and also this year is a very nice number. They fit some models and produce the estimated effort. Okay, here's our code base developed. This is when I joined. And this is when people decided that half of my code wasn't so good. But yeah, we got a quite nice increase in trend. And yeah, I mentioned we're mostly written in C++, but we got some nice interfacing going on. I'll talk about it. So the library itself is mostly just like things like scikit-learn. It's mostly a collection of black box algorithms that you can apply to your data problems. So you open your textbook and you want to learn about machine learning. You first see, okay, supervised learning. We got some pairs x and y. And we want to predict some labels for something we've seen, and we want to train our classification methods on this. So all these methods, all these textbook methods, are implemented in Shogun. And all of them are implemented under a kind of nice unified interface, so that it's easy to use them, easy to compare them, easy to learn about them. Same goes for regression. So originally, back when the library was initiated, so support vector machines was the hype. Today it's something else. And so a bit of focus traditionally in the library was on the support vector machine, so we got some super cutting edge implementation in there and kind of hold the torch for like the most largest collection of these methods. But now we also got GPs and logistic regression and easier things, and same goes for regression, and same goes for all these methods for unsupervised learning that you want to try out when you first deal with your data science problem. Well, all machine learning, so I don't really need to talk about this. But an interesting one is maybe this one here. So one of our developers is this guy who lives in the nowhere in Russia. He really liked the MATLAB toolbox for dimensionality reduction, so he just cloned it. We got all these methods also in Shogun. Yeah, and lots of things like ICA and all these all these it's almost like a pre-processing steps. If you do data science, it's quite useful to have them. And this is all under a unified interface. So apart from these textbook methods, also we got some researchers putting their code into Shogun. So for example, I do research in kernel-based hypothesis testing and all this, like proper large-scale hypothesis testing. All this goes in Shogun. We had people like this guy from Germany, Marius Kloft, he did lots of research on multiple kernel learning. All this stuff is in Shogun. Recently, we integrated some more sophisticated methods on structured output and metric learning through Sum of Code. Currently, I'm working a lot with a guy called Imtiaz Khan, who every year releases 3 new variational methods for latent Gaussian models, and we got them in Shogun. We got a deep learning project recently where you can stack up layers of neurons, connect them, and press a button, and you get a neural network, and you can train it with gradient descent. So that's quite nice. And another thing we have, because we're written in C, so we have the ability to interface with other projects. So for example, in 2011, I think, we had a Sum of Code project where a guy wrote an interface to VW. It's a bit older these days, but I think this is a great opportunity to maybe collaborate. Also, we have an interface to liblinear, so it's very easy within Shogun to run a classifier from VW and liblinear, cross-validate them, and compare them. It's just a couple of lines of code because all this is embedded into our interface. We got recently started writing some super nice tutorials using IPython notebooks. They're all on our website, so just have a look. There's about 20 of these notebooks where you can see like some of the cool stuff we can do. And we require Google Sum of Code students to write these as kind of reports. Picture. Okay, so Shogun originally had like the focus on large-scale learning, but back 10 years ago, large-scale meant something different than today. Back then, it meant that you can deal with lots of data on one computer, which means you want to do proper programming, you want to do proper data structures, and you want to be as fast as possible on one computer. So some of the examples that we have in Shogun is, for example, a splice-side prediction example where we do classification on 50 million examples of 200 million dimensions because we do things properly. And we have the ability to do this because we're written in C++. We also can do like super nice face recognition tasks. We're currently also working on extending we're more thinking about how we can go distributed computing in a nice way. But that's all projects for the future. I'm going to mention this later a bit. So something that's really important if you have all these black box methods is that you somehow have a nice modular framework to connect them and to still get like some reasonable flexibility because well, you have black box methods. So but one thing we can, for example, do, unlike, for example, other toolboxes, is we have a very nice way to represent data. So we just have this data object, and you can have matrices, you can have sparse matrices, you can have collections of strings, you can define streams. Like, for example, the VW framework works then on the stream framework. And in theory, most of the algorithms that we implement, we kind of make sure that this is modular, that you can plug things together in this way. You can also change data types, which is sometimes important, especially if you don't have lots of computer memory. You can just say, okay. Yeah.
So you said in theory. Does that mean that it fails in practice, or does it mean it usually works?
Well, if you train a GP regression, you have to invert your kernel matrix. So if you like for this, you need to hold it in memory. There's no way around it. But for other things, like for example, if you want to do your stochastic gradient descent SVM, then you can give it a matrix, or you can give it a stream handle, and the stream handle can stream in vectors or it can stream in strings that are then passed to a kernel, like that. Okay, it's also super easy to change the data types. That's useful, I think. And we also got a bunch of pre-processing tools, like all this dimensionality reduction that I mentioned is part of the pre-processing framework. We also got other things like, this like decorrelation, removing the mean, filling missing data, and these kind of things. You sometimes want to evaluate methods. So things for doing cross-validation computing, area under the curve, or other things is in there. And this is general. So as I said earlier, I can super easy cross-validate a GP against a linear classifier without any hassle, which is nice. And also select parameters based on brute force or doing some kind of gradient optimization. And we also support various file formats from the low level, which is kind of nice because it's unified under all the interfaces, which I'll talk about now. In a bit. First, some more technical details is so we've written in C++, And we've written in what I call proper C++, which means the entire framework is written in this. It's not just that we take like very isolated methods, say matrix multiplication, and do it in C++ like you can do it in Python. We built the whole framework in this, and this means that we can be a bit more efficient in the sense how we set things up. We can have a high throughput of objects without having problems about this. Well, the downside is we have to deal with memory by hand, and we got some tools for this. But this comes with the advantage that we can build the whole framework in this C language, which makes it quite slim to use. And also we can have this unified interface under all the languages. Yeah, and another thing, I mean, people have been talking about this a lot, but we also, we use Eigen and LAPACK mainly for linear algebra, and also MP, OpenMP and threading. But what we're kind of trying to do, we're trying to isolate the backend for computation from the algorithms. So we have like a little, set of operations, linear algebra, say matrix factorizations, and then you can decide when you install Shogun whether you want to do this on your GPU or whether you want it on your CPU or whether you want some hybrid, or maybe somebody comes up with a more clever implementation, and then we can do this also without having to change the algorithms. So in this way we try to be a bit sustainable. If you want to get an idea of kind of the internals of the C code, have a look at this link.
So what's special about Eigen 3?
Sorry?
So LAPACK can solve Eigen, can be an Eigen, already an Eigen solver. So what's special about Eigen?
So the question is, what's special about Eigen? Well, it's just a way in C you can write a matrix algebra code that almost looks like MATLAB. So it's a header-only library. I think probably the Stan guys will talk about this a bit more.
Eigen 3 is very fast. It uses templates deeply.
Yeah.
It does a lot of trait space stuff.
You basically, I mean, if you have ever used this library, it's a horrible pain. If you just want to do a matrix multiplication, you have to pass like 7 arguments to a function, and then, it's hard to debug and all this, and Eigen just makes it a bit nicer. Okay. So now, this is the main selling point of the toolbox, so we don't think it's a good idea to tell people which programming language to use the toolbox from. So we just support all of them. And this sounds ridiculous and unfeasible, but we've come up with an automatic way to do this. So here's how it works. We use this super cool open source project for this. If I write a new algorithm, what I do is I write the C++ class to do it. And it's a class, I can instantiate it, it has a bunch of methods, some interfaces. The Shogun people were really nice and wrote like all these type maps. So we have type maps that directly map the memory from a NumPy array to, say, a C array without copying things around. So this is all works directly on the memory. And then I just add my class to the list of classes that I want to expose, and then I press a button. And then what I get is wrapper classes and interface files, so that I can use my class from all the languages that we support. And this is super cool because whenever somebody adds something new to Shogun, we got this available from all the classes. Whenever we bind to another external open source project, this is all available from all these classes. So through Shogun, it's super easy to use liblinear from any of these languages under the same interface. And I think that's very useful. Okay, let me give you an example. So here's some C code that's like a skeleton how Shogun code looks like in C. So you get some includes, you get a namespace, you initialize, you exit. Okay, that's the skeleton, it's pretty standard. So here I do a super old school example, Gaussian kernel SVM. I define some training data. Here I would put in some, it has a type, it has like a data type. It's a class, I instantiate it. Here I would plug in some matrix, but I don't have so much space here. I define some test features, I define some labels, I define a kernel, I define an SVM object, I give the objects that I've defined before, I call a method, I give the method something, I call another method to apply to test data, I collect the results, C is a strongly typed language, I have to cast, I print the prediction, I free the memory. Okay, fine. So now let's look at Python. So it's quite similar, the structure is quite similar. So I import, I define the objects, I call methods on the objects, I print. So the modular interfaces can't be templated because languages like Python don't support templates. But that's fine. So here I plug in a NumPy array now rather than a C array. And in Python you instantiate things like this, and in Python you call methods with a dot, but the method is really the same, and I print. So Python starts indexing vectors at 0. So this is how I print. Now I go to Octave, and all that changes. It's really this goes to 1. But I just call methods on objects, and now I pass in just Octave matrices. But I want to emphasize none of this is copied around. This is all we do mapping of the memory. This one is horrible. Yeah. So Java doesn't natively support matrices, linear algebra objects, so we have to import another library, and it's also strongly typed. But it's really the same story. Okay. Okay. So now here's some of the stuff that we have been doing in the last couple of years to kind of make the toolbox a bit more visible. So we really like IPython notebooks. And I already mentioned the collection of notebooks we have on our website earlier. It's kind of a super nice way. You can write a little tutorial, you can have LaTeX, and you can have math, and you can have code, and you can have plots. So we thought it would be really cool if people would be able to use these notebooks and then kind of interactively use them. So what we did is we set up an IPython notebook server on our web server. So when you're on our website, you can press and you click on the notebook, you can press try in cloud, and then you get an interactive session where you can play with the toolbox without ever having to install it. I have to apologize, it's currently broken, but we'll fix it very, very soon. So have a look on this. It's super cool.
Your general method must work.
Sorry?
Your general method for translation between languages, you just press the button.
Yeah, exactly. It's all about the button. That's how I like to present it. It's a bit more tricky practice, obviously. But yeah, this web server is quite nice because you don't need to install the toolbox. You can just play around and kind of have. This is really nice if you just want to really kind of, you have this tutorial and you wanna modify it. I mean, all the Python people kind of, they know this. They can do it also, but we still have all this code that is written in C underneath. So this is on top of this. Yeah. Then we also got something nice. We set up a little JavaScript-based interactive web demo framework. So this is an example of OCR detection that you can do. So you can draw digits, you can classify them. It's also on our website. You can click points together, train an SVM. You can do a GP regression. You can do a sparse GP regression where you set your inducing points and you see how the predictive variance changes, stuff like this. Okay. I mentioned earlier that Shogun is, unlike most of these other projects, it's just really a community project. So here's some of the members of the project. It's quite nice because it's very diverse. So like the people who are active, they live in Siberia, in India, in Singapore, in the US, in Germany or London. And so on. And it's also quite diverse in terms of kind of where these people are. So I just started my PhD. We got some undergraduates programming for us. This guy is professor in Göttingen for machine learning and data security, I think, yeah. And it's a really cool team. And so the project is a nice opportunity to bring lots of people together and learn from each other over borders, which is one of my main motivations to work in it. Most of the other people said this, but we also got a super active mailing list. So come tell us your questions, tell us what you like, what you don't like. We have an IRC where developers hang around. Yeah, just come say hello. And this is what really pushes the project and the community, is this Google Summer of Code. Is anyone who doesn't know this program? Okay, all of you know it. So this year we got 8 students. They worked for 3 months on projects that we thought about. They got a nice stipend for this. Especially the guys in India, they are super happy about this money. I mean, if you live in New York or London, this is nothing. But if you live in, somewhere in South India, this is a lot of money. This is super cool. And in particular, we're always looking to push this further. So, for example, this year we had this deep learning project, and even though we can't really compete, with like deep learning labs that are pushing their libraries outside, we can still have people learn about the stuff. So students implement the stuff, learn about it, but also this will be useful for other people to play with it, because all this code is being embedded in this very general framework. So it will be very easy to say, compare your favorite deep learning algorithm against your favorite non-deep learning algorithm for classification, right? So one of the things I'll be talking about a bit later with the future, we want to try to push that this toolbox is used in education, because it's kind of very general and brings things together. And for this, we always look for people who are willing to mentor open source students to implement stuff for us. Also, if you have a super sophisticated algorithm, just tell us, we'll have it. So yeah, we need help. We're horribly under manpowered. So we really appreciate feedback. We really appreciate if people report bugs or fix bugs, or if you know how to do proper C++ software engineering. We also appreciate this, because we have lots of problems. If you like to write documentation about machine learning algorithms, come to us, write a notebook. It's nice. It's really fun actually to play with this stuff. And it all goes to the website. If you have a website developer, it's nice. If you have like a nice algorithm, come tell us. If you want to join as a mentor in this case, I guess, come join us. And we also need money for infrastructure, workshops, hacks. So we just had a workshop just in Berlin a couple of weeks ago. We had our second workshop that we organized. There were a couple of people there. We did some hacking. It was very nice. We recorded it. It's on YouTube. We're planning to do like a hack sprint where we bring together lots of people interested in this project, hack a bit. And we are really interested also in collaborating with other projects, but more on this maybe in private discussions. Thanks.